Today we're going to start chapter 14. We're going to take a look at Ka, which the capital K, remember, is an equilibrium constant, and the A stands for an acid. So acid dissociation constant. Back in chapter 4, we talked about strong acids and we talked about weak acids. And if you remember from before, strong acids completely dissociate or completely ionize. So they split up into their ions. So if we take a look here, if we have strong acid, like maybe HA, then that means that the HA will completely split into H plus ions and A minus ions in equal proportions based on the mole ratio, 1 to 1. Now, if we take a look here, if we have a weak acid, they only partially dissociate. That means that some of the molecules of HA will split up in ions, but the majority of them will not. And so we'll have several molecules of HA floating around, and then we have in a 1-to-1 ratio the same amount of H plus and A minus. So in this case, we would actually have in strong acids only H plus and A minus present, and then weak acids we would only have we'd have a greater proportion of the molecules. Now keep in mind, now this was absolute, but remember when we're talking about equilibrium with the K, the equilibrium constant, it's a dynamic process. So some of the molecules are actually reforming into the molecule. Some of the ions are reforming into the molecule, and then vice versa. But the majority in a strong acid, the majority of the products will be H plus and A minus, and they'll be made. And so let's take a look at that in terms of Ka values, or equilibrium constant values. If we write the equation for a strong acid and we dissociate it, what do we dissociate it in? Well, back in chapter 4, we dissociate it in water. So we'll take HA and we'll add it to water, and we'll use a double arrow because it is a dynamic process still with acids when you put them in water. And then, just like we talked about before back in chapter 4, remember, the acids are proton donors. So the acid's going to donate an H plus to the water, and then we'll end up with H3O plus A minus. Now, if you're keeping track at home, remember the acid is aqueous, the water is liquid, the hydronium is aqueous, and the conjugate base is aqueous also for physical states. So if we're writing the equilibrium expression for this, we can actually simply write, remember, products over reactants, this is already balanced. We'll put the concentration of H3O plus times the concentration of A minus over the concentration of HA, which is just a generic formula for an acid. So if it's a strong acid and we're dissociating it, what would happen to the K value? Well, we can put in Ka because this is acid dissociation. So this is just still an equilibrium constant, just dealing with an acid. So for a strong acid, what would we make more of? Well, it should completely ionize, so we should make more products. So we should have more of the ions, or almost all the ions get made. So what should happen to the K value in terms of this? Should it be greater than 1 or less than 1? If you said that for a strong acid, the K value is greater than 1, then that's correct. So some strong acids, like you have hydroiodic acid or hydrobromic acid, they have a Ka value on the magnitude on the order of 10 to the 9th power, 10 to the 6th power, which is pretty big. Nitric acid still has a Ka value of 24, which is still greater than 1. So that means that for those strong acids, you would make a lot of the products. In this case, the products are the ions. So it would support the dissociation. Now, what if we switch this and erase this instead of strong, made this weak? And just like magic, weak appears. And the equation for dissociating a weak acid would be the same, except what would you expect the Ka value to be? Well, since weak acids only partially dissociate, only some of the ions are made. So the Ka values should actually be less than 1. So it should be a relatively small number. So if it's less than 1, which is bigger, the numerator or the denominator? Well, the denominator is bigger, so then that is a larger number. So that means that we would have more molecules as opposed to the ionized form, as opposed to H3O plus and A minus. Now, I also wanted to show you just a simple way of writing this instead of using the water, because if we notice, we make hydronium here, which also works too. And like magic, I took away the water, but do note the water is still present in here because it's aqueous, and this says that there's water. So I didn't necessarily have to write the water here, but I could have. And so what happens is it'll still split apart into ions. So we'll get H plus and A minus and HA over here, and we still have equilibrium. We have a reversible reaction here. So, and then instead of hydronium, we have H plus. Now, for the purposes of this class, remember, these are always present in water. So hydronium could be H3O plus, and then or we could have H plus, and then they would mean the same thing, especially with acids and bases and pH, which we will go over tomorrow.